Tonight we're going to explore the closest black hole to the Earth, an object that sits much nearer to us than almost anyone realized, that we cannot see at all, and that, by the rules we thought we understood, should not even exist. For a long time, when we imagined black holes, we imagined them far away, distant monsters at the centers of galaxies, or dramatic objects in violent binary systems thousands upon thousands of light years across the galaxy. Betrayed by the X-rays, they scream as they devour a companion star. The black holes we knew about were the loud ones, the bright ones, the ones tearing matter apart and blazing with the energy of it. And they were, comfortingly, very far away. The nearest one we could confidently point to was thousands of light years off, in the crowded inner reaches of the galaxy. And then, in 2022, astronomers found one much closer. A black hole only about 1,600 light years away, in our own quiet corner of the galaxy, practically next door by cosmic standards. They named it simply Gaia Black Hole 1. And it was unlike the black holes we had known before. It was not screaming in X-rays. It was not tearing apart a companion. It was completely silent, completely dark, giving off no light of any kind. It was a black hole at rest, dormant, sleeping, betrayed not by any radiation, but only by the gentle wobble it produced in the motion of a single ordinary star, a star much like our own sun that circles it in the dark. Tonight, we're going to find this nearest black hole and understand how we found something that gives off no light and sit with the genuine mystery of how it came to be. By the end of tonight, you're going to understand what a black hole at rest actually is, why most of the black holes in our galaxy are invisible, and how astronomers managed to find one that emits nothing at all by watching the dance of the star that orbits it. You are going to understand why this particular black hole poses a real puzzle, why the way it sits with its companion star does not fit the story we tell about how such pairs are supposed to form, why, in the words of the astronomers who found it, it is not easily explained by anything we know, and you are going to understand the larger and stranger truth that this discovery points toward, that our galaxy may be filled with 100 million of these dark, silent, sleeping black holes, almost all of them invisible, scattered through the stars, including, it now seems, in our own quiet neighborhood. This is a journey to the nearest of all the dark monsters, a black hole next door, dormant and silent and strange. There is no need to follow every number. There is no test at the end. The only thing tonight asks is that you let your body grow still while we drift, together, toward a sleeping black hole 1,600 light years away, and the ordinary star that circles it in the dark. Before we begin, if you find that these slow journeys through the real universe help to quiet your mind at the end of the day, take a moment to subscribe so the next one can find you when you need it. If you are listening on Spotify, the follow button does the same quiet work, and it helps these long drifts through the dark reach more people than you would think. That is all. Settle in, lower the lights, let your breathing slow. Now let's begin. We start with the strangeness of trying to find a thing that gives off no light at all, because that is the first puzzle, the one we had to solve before we could find this nearest black hole. How do you find something that is, by its very nature, invisible? Let me set the scene, because it is the heart of why this discovery was so hard and so clever. A black hole is, famously, black. It gives off no light. Its defining feature is that nothing, not even light, can escape from within it. So a black hole sitting alone in space doing nothing is one of the most genuinely invisible objects it is possible to imagine. You cannot see it directly, ever. There is nothing to see. The black holes we had found before were not really exceptions to this. We did not see those black holes either. What we saw was the matter falling into them, the gas torn from a companion star, heated to millions of degrees as it spiraled inward, blazing in X-rays before it vanished forever. We never saw the black hole. We saw its violent meal, and if a black hole is not eating, If it sits quietly with nothing falling in, then there is no meal to see, no X-rays, no light, nothing at all. It becomes truly, completely invisible. And most black holes, it turns out, are exactly like that. Quiet, dark, sleeping, invisible. By the end of tonight, you will appreciate how recent our acceptance of black holes really is, because for most of the history of physics, even the greatest minds doubted that such things could possibly exist. And the story of how the idea was finally accepted is a humbling one. The mathematical possibility of a black hole emerged surprisingly early in 1916, just months after Einstein published his theory of gravity. A physicist named Carl Schwarzschild, working out the equations while serving on the front lines of the First World War, found a solution that described what would happen if matter were compressed into a small enough space. The equations described a region from which nothing could escape, with a boundary, the event horizon, at a specific distance from the center. The mathematics of a black hole had appeared almost immediately in the new theory of gravity. Schwarzschild died of illness a few months later, before the implications of his work were understood, and the strange object that fell out of his equations sat in the theory like a splinter no one wanted to touch. For decades, most physicists, including Einstein himself, did not believe that black holes could actually form in nature. The mathematics permitted them, yes, but surely, they thought, something would prevent matter from ever actually collapsing that far. Some unknown force, some pressure, some mechanism would halt the collapse before a black hole could form. Einstein even wrote a paper arguing that black holes could not exist in reality. The idea was too strange, too extreme, a region where space and time broke down, a hole in the fabric of the cosmos. It seemed more like a mathematical curiosity than a real possibility. For a long time, the black hole remained a thing of equations, doubted by the very people who understood the mathematics best. It took most of the 20th century for the doubt to dissolve. Through the 1930s and beyond, physicists worked out that there was, in fact, no force that could halt the collapse of a sufficiently massive star. The mathematics was relentless. If a star was massive enough, nothing could stop it from collapsing all the way into a black hole. And then, from the 1960s onward, astronomers began finding objects in the sky that nothing but a black hole could explain. The X-ray binaries like Cygnus X1, the quasars powered by supermassive black holes, the orbits of stars around the dark center of our galaxy. The evidence accumulated until the doubt became impossible to maintain. By the end of the century, black holes had gone from a doubted mathematical curiosity to one of the best established objects in astronomy. The term black hole itself, now so familiar, was only coined in the 1960s, a vivid name for the strange object the equations had described half a century before. So when we find the nearest black hole to the Earth, 1,600 light-years away, we are confirming, in our own neighborhood, the reality of an object that the greatest physicists once doubted could exist at all. Gaia Black Hole 1 is a real nearby example of the very thing Einstein argued against. A region where gravity is won so completely that not even light escapes. A hole in the cosmos, sitting quietly in our own galactic backyard. The doubted curiosity of 1916 has become the dark sleeper next door, found by the wobble of a star, a century after the equations first hinted that such things might be. No one expects that black holes were once doubted by the very physicists who understood their mathematics, including Einstein himself, but that is the history. No one predicts that the strange object falling out of the equations in 1916 would take most of a century to be accepted as real, and absolutely no one anticipates how finding the nearest black hole confirms in our own backyard the reality of an object once thought too strange to exist. The doubted curiosity become the dark sleeper next door. Before we go further, let us make sure we really understand what a black hole is, because the word is familiar, but the thing itself is genuinely strange, and the strangeness matters for everything that follows. A black hole is, at its simplest, a region of space where gravity has become so strong that nothing can escape from it, not even light. To understand how that can happen, think about what it takes to leave any massive object. To launch a rocket off the Earth, you have to give it enough speed to overcome the Earth's gravity, what we call escape velocity. For the Earth, that speed is about 7 miles per second. For a more massive object, the escape velocity is higher. Now imagine compressing an object's mass into a smaller and smaller space. As it gets denser, the gravity at its surface grows stronger, and the escape velocity rises. Compress it enough, and the escape velocity reaches the speed of light. And since nothing can travel faster than light, nothing can escape. You have made a black hole. The boundary of a black hole, the point of no return, is called the event horizon. It is not a solid surface. It is a line drawn in space, marking the place where the escape velocity reaches the speed of light. Cross it, going inward, and you can never come back. Because to come back, you would have to travel faster than light, which nothing can do. Everything inside the event horizon is cut off from the rest of the universe forever. Light that crosses it never comes back out. That is why a black hole is black. Not because it is made of dark material, but because it is a region from which no light can ever escape. The event horizon is the surface of darkness, the edge of the region we can never see into. For a black hole of 10 solar masses, like Gaia BH1, the event horizon is small, only about 40 miles across. Think about that. The mass of 10 suns, more than 3 million times the mass of the Earth, packed inside a sphere only 40 miles wide, smaller than many cities. The density is almost beyond comprehension. And around that tiny sphere of darkness, the gravity is so extreme that it captures light itself. The black hole is small, but its gravitational influence reaches out far beyond the event horizon, holding its companion star in orbit at the distance of the Earth from the Sun, 1,600 light-years away, exactly as the visible mass of 10 suns would. And here is the thing that makes a black hole so different from any other object. With a star or a planet or any normal body, you can imagine going to its surface, standing on it, touching it. A black hole has no surface in that sense. There is the event horizon, the boundary of no return, but that is not a solid thing. It is just a line in empty space. Cross it, and you keep falling inward toward the center, where, by our current understanding, all the mass is concentrated into a point of infinite density that our physics cannot fully describe. A black hole is not a dark object sitting in space. It is a place where space and time themselves are so warped that the ordinary rules break down. A region of pure gravity, a hole in the fabric of the cosmos. No one expects that compressing mass into a small enough space would make a region from which not even light can escape, but that is exactly what a black hole is. No one predicts that 10 suns worth of mass could fit inside a sphere 40 miles across, smaller than a city, yet hold a star in orbit from 1,600 light-years away. And absolutely no one anticipates how a black hole is not really an object at all, but a place, a region where gravity is won so completely that space and time break down, and nothing that enters can ever return. So how do you find an invisible thing? You do not look for the thing itself. You look for its effect on the things you can see. And the thing a black hole cannot hide, no matter how dark and silent it is its gravity. A black hole has mass, a great deal of it, packed into an incredibly small space, and that mass pulls on everything around it, exactly as any massive object does. It cannot turn off its gravity. And so, if a black hole has a companion, a star orbiting it, that star will feel the black hole's pull and will move in response to it. The star will trace out an orbit around the unseen mass, circling a point in space where there appears to be nothing at all. And if you watch that star carefully enough, precisely enough, you can see it moving in a way that only makes sense if something massive and invisible is there, tugging it around. You cannot see the black hole, but you can see the star dancing with its dark partner, and from the dance you can deduce the partner's presence, its mass, its nature. This is the method that found Gaia BH1, and it was made possible by an extraordinary spacecraft, the one the black hole is named after. Gaia is a European space telescope with a single, almost impossibly ambitious mission: to measure the positions and motions of stars, not a few stars, nearly 2 billion of them. Gaia has been mapping the positions of nearly 2 billion stars across our galaxy, repeatedly, over years, with a precision so fine it is hard to convey. It can measure the position of a star to an accuracy that would let you, in principle, detect the width of a human hair seen from hundreds of miles away. It watches the stars again and again, building up a record of exactly where each one is and how it is moving, the most detailed map of our galaxy ever made. Tonight, we're going to spend some time on the Gaia spacecraft itself, because it is one of the most quietly remarkable machines humanity has ever built, and without it, the nearest black hole would still be invisible to us. Gaia was launched by the European Space Agency at the end of 2013, and it has a mission that sounds almost absurdly ambitious when you first hear it. Its job is to make a map. Not a map of one patch of sky, not a survey of a few interesting objects, but a three-dimensional map of our entire galaxy, by measuring the precise positions, distances and motions of nearly 2 billion stars. 2 billion. It is by far the most detailed and most ambitious map of the Milky Way ever attempted, a census of a sizable fraction of all the stars we can see. The key to Gaia is precision, and the precision it achieves is genuinely difficult to comprehend. To map the galaxy in 3 dimensions, Gaia must measure not just where each star appears in the sky, but how far away it is and how it is moving. It does this by measuring star positions with extraordinary accuracy, repeatedly over years, watching how each star shifts. The accuracy is so fine that Gaia can measure angles on the sky, equivalent to seeing the width of a human hair from hundreds of miles away, or, by another comparison, the size of a small coin on the surface of the moon. With that precision, tiny motions that no previous instrument could detect become visible. The slow drift of stars through the galaxy, the tiny annual wobble caused by the Earth's own motion around the Sun, which reveals each star's distance, and crucially, the small wobbles of stars being tugged by unseen companions. To find a black hole, Gaia looks for that last kind of wobble. A star orbiting an invisible massive companion does not move in a straight line through the sky. It traces out a tiny, regular repeating wobble, a little ellipse superimposed on its overall motion as it circles the unseen mass. For most of history, such wobbles were far too small to detect, but Gaia's precision is fine enough to catch them. And so, hidden in the motions of 2 billion stars, Gaia recorded the wobbles of stars orbiting dark companions, and astronomers, sifting through that vast catalogue, found the ones whose wobbles indicated something massive and invisible. Among them was the sun-like star orbiting Gaia Black Hole 1. There is something I find genuinely moving about this. Gaia is not a black hole hunter. It was not built to find black holes. It was built to map the galaxy, to measure where the stars are and how they move, a vast patient act of cosmic cartography. And in the course of that patient mapping, in the precise measurement of 2 billion stellar positions, it happened to catch the gravitational fingerprints of the nearest black holes to the Earth, hidden in the wobbles of ordinary stars. The discovery of the nearest black hole was, in a sense, a side effect of the most ambitious mapping project in the history of astronomy, a treasure found while making the map. No one expects a spacecraft built to map the galaxy to also be the instrument that finds the nearest black holes, but Gaia's precision made it so. No one predicts that the gentle wobble of a star, far too small for any previous instrument to detect, would reveal an invisible black hole 1,600 light-years away. And absolutely no one anticipates how the patient work of cosmic cartography, measuring 2 billion stars one position at a time, would turn up, almost incidentally, the closest dark monsters to the Earth. And with that precision, Gaia can do something remarkable. It can detect the tiny wobble of a star being tugged by an unseen companion. If a star is orbiting something invisible, its position in the sky will trace out a small, regular wobble over time, a little ellipse, as it circles the unseen mass. Gaia, measuring star positions with its extraordinary precision, can detect these wobbles. And among the nearly 2 billion stars it has measured, astronomers went looking for stars wobbling in a particular way, the way that would indicate they were orbiting something massive and dark. They were hunting, in effect, for the gravitational fingerprints of invisible companions, hidden in the motions of ordinary stars. Tonight, we're going to go a little deeper into exactly how Gaia measures a star precisely enough to detect an invisible companion, because the technique is beautiful, and it rests on a method astronomers have used for centuries, pushed to an extraordinary new extreme. The foundation is something called parallax. Hold your finger up at arm's length and look at it with one eye, then the other. Your finger appears to shift against the background, because you are viewing it from two slightly different positions, your two eyes. The closer the finger, the bigger the shift. Astronomers use the same trick with stars, but instead of two eyes, they use the two ends of the Earth's orbit. As the Earth travels around the Sun over a year, our viewing position shifts by the full width of the orbit, about 186 million miles. A nearby star, viewed from these two extremes, appears to shift slightly against the more distant background stars. By measuring that tiny shift, astronomers can calculate the star's distance. This is the most fundamental way we measure distances to stars, and it is pure geometry, the same triangulation a surveyor uses. Gaia performs this measurement for nearly 2 billion stars, with precision finer than anything before. But the parallax shift is only part of what Gaia records. Each star is also drifting through the galaxy on its own path, a steady motion across the sky that astronomers call proper motion. And if a star has an invisible companion, there is a third component to its motion, the wobble, the small regular orbit it traces as it circles the unseen mass. So a star's path across the sky, as Gaia records it, is a combination of three things: the annual back and forth of parallax, which reveals its distance, the steady drift of proper motion, which reveals how it moves through the galaxy, and, if present, the small repeating wobble of an orbit around an invisible companion. The art of the discovery lies in separating these three motions. Astronomers take Gaia's precise record of a star's position over years, and they untangle the components. They subtract the annual parallax wobble, the part caused by the Earth's own orbit. They subtract the steady proper motion, the part caused by the star's drift through the galaxy. And whatever is left over, any additional regular wobble, is the signature of an orbit around an unseen companion. For the star orbiting Gaia Black Hole 1, that leftover wobble was clear, a small regular orbit around something invisible, and from its size and period, astronomers could calculate the mass of the hidden companion, the 10 solar mass black hole. This is detective work of the finest kind, and it is worth appreciating. The whole discovery rests on measuring the position of a single star, 1,600 light-years away, precisely enough, over enough time, to detect a wobble far smaller than anything previous instruments could see, and then carefully separating that wobble from the other motions of the star to reveal the gravitational fingerprint of an invisible black hole. It is geometry and patience and precision, the same parallax method astronomers have used for centuries, refined to a degree that lets us weigh the unseeable by the dance of the seen. No one expects the method that finds invisible black holes to be the same ancient triangulation a surveyor uses, but at its heart, that is what Gaia's astrometry is: parallax and proper motion and wobble, measured with extraordinary precision. No one predicts that separating the three components of a star's motion would reveal, in the leftover wobble, the mass of an unseen black hole. And absolutely no one anticipates how the nearest dark monster was found by pure geometry, the patient triangulation of a single star's position, refined to a precision that lets us see the invisible by its gentle pull. And they found one, a star much like our own sun, about 1,600 light-years away that was wobbling, tracing out an orbit around something. And when astronomers worked out how much mass that invisible something had to have to tug the star the way it did, the answer was striking. About 10 times the mass of our Sun, 10 solar masses, packed into something that gave off no light at all. A massive, dark, invisible companion, 10 times heavier than the Sun, circling with an ordinary star in the quiet of our galactic neighbourhood. There was only one thing it could be: a black hole. It is worth knowing that Gaia Black Hole 1 was not the first object claimed to be the nearest black hole, and the history of those earlier claims shows just how hard this kind of discovery really is and how careful astronomers have to be. In recent years, before Gaia Black Hole 1, there were several announcements of nearby black hole candidates, each one greeted with excitement, and each one, in the end, complicated or overturned. One system, a few years earlier, was announced as containing the nearest black hole to the Earth with great fanfare. But when other astronomers examined the data, they came to a different conclusion. They argued that the system could be explained without a black hole at all by an unusual arrangement of ordinary stars. A vigorous scientific debate followed, with different teams reanalyzing the data and reaching different conclusions, and eventually the consensus moved away from the black hole interpretation. The nearest black hole, it turned out, had not been found after all. It had been a false alarm, or at least a genuinely ambiguous case. There were others. Another candidate, sometimes called by a nickname, was proposed as a nearby dormant black hole, found by the motion of a companion star. But again, the interpretation was debated, with some astronomers arguing the companion might be a more ordinary, if unusual, star rather than a black hole. The history of nearby black hole claims in the years before Gaia Black Hole 1 is a history of excitement, followed by careful scrutiny, followed, often, by doubt. Finding a dormant black hole is genuinely hard, and the data can be ambiguous, and ordinary stellar systems can sometimes mimic the signature of a hidden black hole. Astronomers learned, through these episodes, to be cautious, to demand strong evidence before claiming a black hole. This is exactly why Gaia Black Hole 1 was so convincing and so important. The evidence was clean. The wobble of the companion star was clear and well measured. The mass of the invisible companion came out high enough, and the companion star itself was ordinary enough that there was no plausible way to explain the system without a black hole. After the false alarms and the debates of previous years, here at last was a dormant black hole that survived scrutiny, that the community could broadly accept, the first clear, confident detection of one of the silent majority. It was not the first claimed nearest black hole, but it was the first one that held up. There is a lesson in this that runs deeper than black holes about how science actually works. The path to a solid discovery is rarely smooth. It runs through false alarms, ambiguous cases, vigorous debate, claims made and then withdrawn. This is not a failure of science. It is science doing exactly what it should: proposing, scrutinizing, debating, demanding strong evidence, and accepting a result only when it has survived the hardest looking. Gaia Black Hole. One is trustworthy precisely because it came after the false alarms, because it was tested against the lessons those earlier episodes taught, because it survived the scrutiny that the others did not. The nearest black hole was found not in a single triumphant moment, but at the end of a careful, sometimes messy, deeply honest process of getting it right. No one expects the path to finding the nearest black hole to run through false alarms and overturn claims, but that is exactly the history before Gaia Black Hole 1. No one predicts how hard it is to be sure a dormant black hole is really there, with ordinary stellar systems sometimes mimicking the signature. And absolutely no one anticipates how the messy, careful, honest process of proposing and scrutinizing and debating is exactly what makes Gaia Black Hole 1 trustworthy. The first nearby dormant black hole that finally held up. Pattern interrupt. Consider what was actually achieved here, because it is easy to let it slip past. astronomers found a completely invisible object, a black hole that gives off no light whatsoever, not by seeing it, which is impossible, but by measuring, with breathtaking precision, the tiny wobble of a star 1,600 light-years away, and deducing from that wobble alone the presence of a 10 solar mass black hole circling it in the dark. They weighed the invisible by watching the visible dance with it. They found the unfindable by its gravity alone. It is one of the most elegant detective stories in all of modern astronomy. No one expects to be able to find a completely invisible object, but by watching the star that orbits it, astronomers found exactly that. No one predicts that a spacecraft measuring the positions of 2 billion stars would catch, in the wobble of one ordinary sun-like star, the gravitational fingerprint of the nearest black hole to the Earth. And absolutely no one anticipates how elegant the method is, weighing the unseeable by the dance of the scene, finding a black hole not by its light, of which it has none, but by the gentle, undeniable pull it cannot hide. By the end of tonight, you will understand how we found black holes before Gaia, because the contrast shows just how different and how much more representative the dormant black holes are. The first black hole ever confidently identified is a famous object called Cygnus X1, found in the early 1970s. It is a powerful source of X-rays in the constellation Cygnus, the Swan. When astronomers studied it, they found a bright, hot, massive star, and they found that this star was orbiting an unseen companion. By measuring the star's motion, they worked out the mass of the invisible companion, and it came out too high to be anything but a black hole. Cygnus X1 became the first object that the scientific community broadly accepted as a black hole, and it remains one of the most studied. It was so famous that it became the subject of a well-known scientific bet between two prominent physicists. A wager on whether it was truly a black hole eventually settled when the evidence became overwhelming. But notice how Cygnus X1 was found, and how different it is from Gaia Black Hole 1. Cygnus X1 is a loud, feeding system. The black hole there is close enough to its companion star to pull a constant stream of gas from it, and that gas spiraling in heats up and blazes in X-rays, which is exactly what makes it visible across thousands of light-years. We found Cygnus X1 because it is screaming in X-rays, because it is violently devouring its companion. It is a black hole caught in the act of feeding, betrayed by the brilliance of its meal, and for decades, this was the only kind of black hole we could find. The X-ray binaries, the feeding systems, the loud ones. We built X-ray telescopes and scanned the sky for these bright sources, and one by one we found them. A few dozen black holes across the galaxy, all of them feeding, all of them screaming in X-rays. They were dramatic, and they taught us an enormous amount. But they were also, we now understand, deeply unrepresentative. They were the rare cases where a black hole happened to have a companion close enough to feed on. The vast majority of black holes, the ones not in such tight feeding pairs, remained completely invisible to this method. We were finding only the loud minority and mistaking it, in a sense, for the whole. This is why Gaia Black Hole 1 matters so much. It is the first clear member of the silent majority, found not by its violence but by its gravity, not by the X-rays of a meal it is not eating, but by the gentle wobble of a star it merely holds in orbit. It opened a new way of finding black holes, one that does not require them to be feeding, one that can reveal the dormant, dark, silent ones that make up most of the population. The X-ray method found us the loud few. The Gaia method is beginning to find us the quiet many, and the quiet many, it turns out, are the true face of the galaxy's black hole population, the 100 million dark sleepers that the loud feeders only ever hinted at. No one expects the famous black holes we found first, the loud screaming X-ray binaries, to be the unrepresentative exceptions, but that is what they were. No one predicts that for decades we were finding only the rare feeding minority, while the dark dormant majority stayed completely hidden. And absolutely no one anticipates how a new method, finding black holes by the gentle wobble of their companions rather than the violence of their meals, would finally begin to reveal the silent many, the true population, the dark sleepers the loud feeders only hinted at. Let us look closely now at what this object actually is, because Gaia Black Hole 1 is a very different kind of black hole from the ones we knew before, and the difference is the key to everything. Tonight, we're going to let one quiet thought settle over everything else. The thought that changes how the night sky feels once you have truly taken it in, which is this. The sky we look up at is not only the sky we can see. Woven all through it, between and among the visible stars, is a second sky, a dark sky, made of things that give off no light at all. For all of human history, we have known the sky as a field of lights. The stars, the planets, the soft band of the Milky Way, the occasional comet or falling streak, all of them luminous, all of them announcing themselves to our eyes. We drew the constellations from those lights, told our stories with them, navigated by them, set our calendars and our myths by their slow turning. The sky, to us, has always meant the lights in the sky. And it was easy to believe that the lights were the whole of it, that what we could see was what was there, that the dark spaces between the stars were simply empty, simply nothing, the black backdrop against which the real things, the bright things, were arranged. But Gaia Black Hole 1 and the 100 million dark sleepers it represents tell us that the dark spaces are not empty at all. Threaded through the familiar field of lights is a whole population of objects that shine with nothing, that hang in the dark giving off no signal our eyes or telescopes can catch, that are there, massive and real, and yet utterly invisible. For every bright star we can see, there are dark companions, dead stars, dormant black holes, drifting unseen among the luminous crowd. The sky we have always known, the sky of lights, sits inside a larger sky we're only beginning to perceive, a sky that includes the darkness, the corpses, the hidden monsters, the things that do not shine. We have been reading only half the page, the bright half, and the dark half has been there all along, unread. There is something strangely peaceful in that thought, rather than frightening, when you let it settle in the dark of your own room tonight. The sky is fuller than we knew, richer, more crowded, holding not only the lights we have always loved, but the dark things that keep them company, turning silently among them. When you look up now, you can hold both skies at once, the bright one, the familiar field of stars, and the dark one, the hidden population, the dormant black holes and dead stars woven invisibly through the same space, the nearest of them only 1,600 light-years away, a near neighbour in the dark. The night is not emptier than we thought, it is fuller. The darkness between the stars is not nothing, it is full of quiet, sleeping things. And so the discovery of the nearest black hole is not really a discovery of one object. It is a small lifting of the veil on that second sky, the dark sky, the one we are only now learning to see. Gaia Black Hole. One is a single dark thread, the nearest one, pulled gently into view by the wobble of a star. Behind it lie 100 million more, the rest of the dark sky, still unseen, still waiting, turning silently among the lights we know. We have spent our whole history watching the bright sky. Tonight, we are beginning, just beginning, to see the dark one too, and to understand that it has been there all along, the quiet companion of every light we have ever named. No one expects that the familiar night sky, the field of lights we have known for all our history, is only half of what is truly there. But woven through it is a second, darker sky we are only now learning to see. No one predicts that the dark spaces between the stars are not empty at all, but full of dormant black holes and dead stars, the nearest only 1,600 light-years away. And absolutely no one anticipates how the discovery of the nearest black hole is really the lifting of a veil, a first glimpse of the dark sky that has kept the bright one company since the very beginning. The black holes astronomers had found before Gaia were almost all what we call X-ray binaries. In those systems, a black hole and a star orbit very close together, so close that the black hole's gravity pulls a constant stream of gas off the surface of the companion star. That gas does not fall straight in. It swirls around the black hole first, forming a flat spinning disk, and as it spirals inward, friction heats it to millions of degrees, hot enough to blaze in X-rays. So the black hole, though invisible itself, surrounds itself with a brilliant screaming disk of stolen superheated gas. That is what we saw. That is how we found the first black holes, by the X-rays pouring off the matter they were devouring. They were the loud ones, the feeding ones betrayed by the violence of their meals. There is a deeper question hiding underneath this whole story, one worth sitting with, which is what exactly separates a black hole from the other things a dying star can leave behind, and why that boundary matters so much for what we have found. When a massive star dies, the fate of its core depends, more than anything, on its mass. A star like our Sun will end as a white dwarf, an Earth-sized ember of carbon and oxygen, held up against its own gravity by the stubborn resistance of its packed electrons, cooling slowly over the ages. A heavier star, one that ends with a core above a certain limit, cannot stop at the white dwarf stage. Its gravity is too strong, and it collapses further, crushing its protons and electrons together into neutrons, until the entire core becomes a single, impossibly dense ball of neutrons, a neutron star, a city-sized object holding more than the mass of the Sun, a teaspoon of which would weigh as much as a mountain. And there, for a slightly heavier core, the collapse halts again, held up this time by the resistance of the neutrons themselves, crushed shoulder to shoulder, refusing to be squeezed any tighter. The neutron star is the next to last stop on the road of stellar death, the densest thing the universe can make and still hold in balance. But there is a limit even to the neutrons. Pile on enough mass, push the core above roughly 2 to 2.5 times the mass of the Sun, and not even the neutrons can hold. Their resistance, mighty as it is, gives way, and once it gives, nothing remains to stop the fall. There is no known force, no pressure, no resistance left in the universe that can halt the collapse of a core that heavy. It falls and keeps falling, past the neutron star stage, past every limit, collapsing without end, until it has crushed itself into a point of effectively infinite density, wrapped in an event horizon, a black hole. The boundary between a neutron star and a black hole is therefore one of the most important lines in nature. Below it the collapse stops, held by the neutrons, and you get a dense but stable corpse. Above it the collapse never stops, and you get a hole in space-time. This is exactly why the mass of Gaia Black Hole 1 matters so much. At roughly 10 solar masses, it sits far, far above the neutron star limit, 5 times beyond the heaviest neutron star that could possibly exist. It is not a borderline case, not a thing teetering on the edge between one kind of corpse and another. It is unambiguously, decisively past the line, in the territory where only a black hole can exist. There is no version of physics in which a 10 solar mass object could be a neutron star held up by neutron pressure. The neutrons would have failed long before, and so the very mass that we measure from the star's wobble, the 10 solar masses, is itself the proof, placing the dark object firmly in the realm where collapse has won completely, where the event horizon has closed, where the black hole is the only thing that fits. It is humbling to think about that boundary. On one side, the densest stable matter the universe permits, the neutron star, extreme almost beyond imagining, and yet still a thing, still an object with a surface. On the other side, just a little more mass, and matter loses entirely, surrenders to gravity, falls forever, leaving only a region of darkness and a horizon beyond which nothing can be known. Gaia Black Hole. One lives on the far side of that line, well past it, a place where the resistance of matter has been utterly overwhelmed, where there is no surface, no ember, no city of neutrons, only the bottomless fall and the dark boundary around it. The nearest dark object to the Earth is not a dense corpse that gravity merely squeezed. It is a corpse gravity defeated. No one expects that the difference between a neutron star and a black hole comes down to a single sharp limit, a line above which no force in the universe can stop the fall. But that boundary is one of the most important in nature. No one predicts that the measured mass of Gaia Black Hole 1, 10 times the Sun, places it 5 times beyond that limit, far past any doubt. And absolutely no one anticipates how the nearest dark object to the Earth is not a corpse that gravity squeezed into a ball, but a corpse that gravity defeated entirely, collapsing without end into a hole in space-time. Gaia Black Hole. 1 is nothing like that. Its companion star, the Sun-like star that orbits it, is not close enough for the black hole to steal gas from it. The two are separated by roughly the distance between the Earth and the Sun, a comfortable wide orbit, with the star circling the black hole once every 6 months or so. At that distance, the black hole pulls on the star gravitationally, yes, holding it in orbit, but it does not strip gas from it. There is no stream of stolen matter. There is no swirling disk. There is no superheated gas. And so there are no X-rays, no light, nothing to see. The black hole simply sits there, dark and silent, holding its companion at arm's length, giving off nothing. It is a dormant black hole, a quiescent one, a black hole at rest, not feeding, not blazing, just quietly existing in the dark. By the end of tonight, you will have a sense not only of what Gaia Black Hole 1 is now, but of what it may yet become, because this system has a future as well as a past, and that future is one of the stranger things to think about as you drift towards sleep. Right now, the sun-like star and the black hole keep their distance. The star circles in a wide, gentle orbit, roughly the distance from the Earth to our Sun, and at that range it is perfectly safe, untouched, simply orbiting as it has for ages. The black hole is dormant precisely because the star is far enough away that nothing is being pulled off it. No gas streams across the gap, no glowing disk forms. The two simply turn around their common centre, the bright one and the dark one, in quiet balance. But stars do not stay the same forever. Our own Sun, in some 5 billion years, will swell into a red giant, ballooning outward as it exhausts its fuel, growing many times its present size before it sheds its outer layers and fades. The sun-like star in Gaia Black Hole. One will, in its own time, do the same, and when it swells, the careful distance between the star and the black hole may no longer be safe, for when that star expands into a giant, its outer layers will reach farther out into space, closer to the black hole, and the black hole's gravity will begin to pull at them. Gas from the swollen star may start to stream across the gap, drawn toward the black hole, spiraling inward, forming the very disk that is absent now. And when that happens, the dark and silent system will wake. The black hole will begin to feed, and the infalling gas will heat and glow and blaze with X-rays, and Gaia Black Hole 1, dormant for so long, will light up, becoming an active black hole, an X-ray binary like Cygnus X1, loud and bright where it was once silent and dark. The quiet system we see today may be only a phase, a long dormant chapter before a violent awakening still billions of years away. It is a strange thought, that the very silence which hides this black hole from us is temporary, a feature of this particular moment in the star's long life. We happen to be watching during the dormant phase, when the star is ordinary and the black hole is dark and the only sign of the monster is the gentle wobble. But the system has not always been silent, and may not always be. There was the violence of the black hole's birth long ago, when its progenitor star died. There is the quiet now, and there may be a loud and luminous future when the companion swells and feeds the darkness it has circled all along. The dormant black holes we are now finding are not a separate kind of object from the bright ones. They are the same objects caught in a different, quieter season of their lives. So Gaia Black Hole 1 is not a fixed and frozen thing. It is a system in slow motion through time, a star and a black hole bound together through the long ages, passing through phases of silence and, perhaps one day, of fire. The darkness we have found is sleeping, but sleep is not death, and the gentle orbit we measure today is a snapshot of one moment in a story that stretches across billions of years. From a violent birth we did not witness to a fiery awakening we will never see, with only this quiet, dark, dormant present laid open to our instruments. No one expects that the silent black hole next door might one day wake and blaze with light, but when its companion swells into a giant, that is exactly what may happen. No one predicts that the dormant systems we are now finding are the same objects as the bright X-ray binaries, merely caught in a quieter season of their lives, and absolutely no one anticipates how the silence of Gaia Black Hole 1 is only a phase, a long dark chapter between a violent birth in the distant past and a possible fiery awakening in the distant future. And this is why it matters so much, why this dormant black hole is more important, in a way, than all the loud ones we found before. Because the loud feeding black holes are the rare exceptions. For a black hole to blaze in X-rays, it needs a companion close enough to feed it, an arrangement that is relatively uncommon. The vast majority of black holes are not in such intimate feeding pairs. The vast majority are like Gaia Black Hole 1, dormant, isolated or in wide orbits, not feeding on anything, and therefore completely dark and silent. The black holes we had found were the loud minority. The dark, sleeping majority had been invisible to us, undetectable, hidden. Gaia Black Hole 1 is the first clear glimpse of that hidden majority, the first of the quiet ones we have managed to find, and it is, fittingly, the nearest black hole to the Earth that we know of. We have said that a black hole gives off no light and cannot be seen directly, and that is true. But there is one way we have managed to come as close as physics allows to actually seeing one, and it is worth telling, because it is one of the great achievements of recent astronomy, and it shows the difference between the dormant black holes near us and the great ones at the centres of galaxies. You cannot photograph a black hole itself because it emits no light. But if a black hole is surrounded by bright hot gas, you can photograph the gas, and in the middle of it, you can see the silhouette, the shadow, the dark circle where the black hole sits, where its gravity has swallowed the light. This is exactly what a team of astronomers achieved, using a network of radio telescopes spread across the entire Earth, linked together to act as a single telescope as large as the planet. In 2019, they released the first such image of the giant black hole at the centre of a distant galaxy called M87, a black hole billions of times the mass of the Sun. The image showed a ring of glowing gas, and in the centre, a dark circle, the shadow of the event horizon, the first picture humanity had ever taken of the silhouette of a black hole. A few years later, they did it again, this time for the black hole at the centre of our own galaxy, Sagittarius A star, a black hole about 4 million times the mass of the Sun. Another ring of glowing gas, another dark shadow at the centre, a portrait of the monster at the heart of the Milky Way. These images were tremendous achievements, the closest we have ever come to seeing a black hole, the dark shadow at the centre of a bright glowing ring, captured by a telescope the size of the Earth. But notice the difference between these black holes and Gaia Black Hole 1. The black holes that have been imaged are supermassive, millions or billions of times the mass of the Sun, sitting at the centres of galaxies, surrounded by bright glowing gas that makes their shadows visible. Gaia Black Hole 1 is a stellar black hole, only 10 times the mass of the Sun, and it has no bright glowing gas around it, because it is not feeding. It is far too small and far too dark to ever be imaged the way the great central black holes were. Even though it is vastly closer, only 1,600 light-years away compared to the millions or billions of light-years to the imaged ones, it cannot be photographed, because it has nothing glowing around it to reveal its shadow. The dormant black holes near us are, in a sense, even more hidden than the distant giants, because they have no bright surroundings to betray them. So we have two very different ways of approaching the invisible. For the great supermassive black holes at the centres of galaxies, surrounded by glowing gas, we can photograph the shadow, the dark silhouette in the bright ring. For the small dormant stellar black holes near us, with nothing glowing around them, we cannot see even a shadow, and must instead find them by the gravitational wobble of their companions. The distant giants we can almost see. The nearby sleepers we can only weigh by their pull. The closest black hole to us is, paradoxically, far less visible than the monstrous ones millions of light-years away, because it is dark and quiet and they are wrapped in fire. No one expects that we could photograph the shadow of a black hole at all, but with a telescope the size of the Earth, we have done it for the giants at the centres of galaxies. No one predicts that the nearest black hole to us, vastly closer than the imaged ones, would be impossible to photograph, because it has no glowing gas to reveal it. And absolutely no one anticipates how the dark, dormant sleepers near us are in their silence, even more hidden than the distant giants wrapped in fire. Let me give you a sense of the object itself. It is about 10 times the mass of our Sun. All of that mass crushed into a black hole only a few dozen miles across, smaller than a city. An object so dense and so compact that its gravity prevents even light from escaping. Around it, at about the distance of the Earth from the Sun, circles a star quite similar to our own, a little less massive. An ordinary star that could, in another system, have planets and perhaps even life. But this star has a dark companion. It circles every 6 months, a point in space where there is a black hole, 10 times the mass of the Sun that it cannot see, that gives off no light, that simply holds it in its gravitational grip and turns with it through the dark. A sun-like star in an Earth-like orbit around a black hole. That is Gaia Black Hole 1, the nearest black hole to us, 1,600 light-years away. There is a subtle but fascinating question lurking behind the mass of these black holes, and it concerns the boundary between a black hole and the slightly less extreme object it could have been instead, a neutron star. The boundary turns out to hide one of the genuine puzzles of the field. When a massive star collapses at the end of its life, the outcome depends on how much mass ends up in the collapsing core. If the core is below a certain limit, it collapses into a neutron star, an object the size of a city holding more than a sun's worth of mass, incredibly dense but not quite dense enough to become a black hole. If the core is above that limit, nothing can stop the collapse, and it becomes a black hole. So there is a dividing line, a mass boundary, between the heaviest neutron stars and the lightest black holes. Neutron stars top out at somewhere around 2 to 2.5 times the mass of the Sun. Black holes, we long thought, begin at around 5 solar masses, and in between, from about 2.5 to 5 solar masses, there seemed to be a strange gap, a range of masses where we found very few objects at all, neither neutron stars nor black holes. Astronomers called this the mass gap, and it was a real puzzle. Why should there be a shortage of objects in that middle range? If stars collapse across a continuous range of masses, you might expect a continuous range of remnants, with neutron stars shading smoothly into black holes. Instead, there seemed to be a gap, a missing population in the middle, as though nature preferred to make either a clear neutron star or a clear black hole, but rarely anything in between. The cause of the gap is not fully understood, and it connects to the detailed physics of how stars collapse, how the supernova explosion succeeds or fails, and how much matter falls back onto the remnant. It is one of the open questions about stellar death. Gaia Black Hole 1, at about 10 solar masses, sits comfortably above the gap, a clear and ordinary black hole. But the broader effort to find dormant black holes by their companions is exactly the kind of work that could fill in the gap, or confirm it. By finding more and more of these dark remnants, and measuring their masses precisely, astronomers can map out the full distribution, from the heaviest neutron stars through the gap and into the black holes. Each new dormant object found by its companion's wobble is a data point in this map, and recent discoveries, by Gaia and by other means, have begun to find objects right in the gap, mysterious dense remnants of 2 or 3 solar masses, neither clearly neutron star nor clearly black hole, suggesting the gap may not be as empty as we thought. So the search that found the nearest black hole is also, quietly, addressing one of the deeper puzzles of stellar death, the question of what nature makes when a star collapses, and why there seems to be a preference for certain outcomes over others. Gaia Black Hole. 1 is a clear black hole, well above the gap. But its discovery is part of a larger effort that is slowly mapping the full range of stellar corpses, from neutron stars through the puzzling gap and into the black holes, building, object by object, a picture of exactly what the deaths of massive stars leave behind. No one expects there to be a strange gap in the masses of stellar remnants, a shortage of objects between the heaviest neutron stars and the lightest black holes. But that is what astronomers found. No one predicts that the search for dormant black holes by their companions would also help map this gap, filling in the puzzling middle range. And absolutely no one anticipates how the discovery of the nearest black hole connects to one of the deeper open questions of stellar death, the mystery of what nature makes and what it leaves missing when a great star finally collapses. A natural curiosity arises when we think about a black hole only 1,600 light-years away. What would happen if you could somehow travel there and fall in? It is a question worth answering, not because anyone ever will, but because the answer reveals just how strange these objects are. Falling into a stellar black hole like Gaia Black Hole 1 would be, by the standards of the universe, a violent affair, and the reason is its small size. A black hole's gravity grows enormously stronger as you approach the center, and for a small black hole, the gravity changes very steeply over a short distance. This means that as you fell in, feet first, the gravity pulling on your feet would be noticeably stronger than the gravity pulling on your head, because your feet would be closer to the center. That difference would stretch you, pulling you out lengthwise while the funneling of the gravity squeezed you in from the sides. Astronomers have a vivid, almost comical word for this: spaghettification. You would be stretched into a long, thin stream, like a strand of pasta torn apart by the difference in gravity across your body, long before you ever reach the center. For a small black hole like Gaia Black Hole 1, this stretching would become lethal even before you cross the event horizon. The gravity changes so steeply around a 10 solar mass black hole that you would be torn apart while still outside it, in the region where the gravitational difference across your body became unbearable. There would be no gentle crossing, no moment of floating through the event horizon intact. For these small stellar black holes, the approach itself is fatal, the stretching beginning while you're still well outside the point of no return. It is by any measure one of the more unpleasant ways the universe offers to die, and there is the matter of time, which behaves strangely near a black hole. The intense gravity warps not just space but time, slowing it down. To a distant observer watching you fall, your descent would appear to slow as you approach the event horizon, your image stretching and reddening and freezing, never quite seeming to cross, hovering forever at the edge. But to you falling, time would feel normal, and you would cross, if the stretching had not already destroyed you, in a finite time, into the region from which nothing returns. The two perspectives, the falling and the watching, would never agree on when or whether you crossed. Time itself bends around these objects, so that the same fall takes a finite moment for the one falling and an eternity for the one watching. I describe all this not to frighten, but because it conveys how genuinely extreme these objects are, even the small dormant ones near us. Gaia black hole. One may be silent and dark and harmless from 1600 light-years away, holding its star in a gentle orbit. But up close, it is one of the most violent environments the universe permits, a place where gravity stretches you into pasta before you arrive, where time itself bends and freezes, where space and time break down entirely beyond the event horizon. The nearest black hole is harmless at a distance, but it is no less a monster for that, an object of genuine extremity, sleeping quietly in our galactic neighborhood. No one expects that falling into a black hole would stretch you into a long thin strand like pasta, but for a small one like Gaia Black Hole 1, that is exactly what would happen even before you reached it. No one predicts that time itself would bend so strangely near a black hole that the falling and the watching would never agree on when you crossed. And absolutely no one anticipates how the nearest black hole, harmless and silent from a distance, is up close one of the most violent and extreme environments the universe permits. No one expects most black holes to be dark and silent and invisible, but that is exactly what most of them are. Dormant, not feeding, giving off nothing. No one predicts that the black holes we found first, the loud screaming X-ray binaries, would turn out to be the rare exceptions, while the true majority sat hidden in the dark. And absolutely no one anticipates that the nearest black hole to the Earth would be one of these quiet ones, a sleeping 10 solar mass black hole holding an ordinary sun-like star in a wide and gentle orbit, 1600 light-years away, betraying itself only by the dance of the star that circles it. Tonight we're going to consider a fair and important question, the kind a careful skeptic would ask, which is this. How can astronomers be so sure that the dark thing at the centre of that star's orbit is a black hole, and not simply a faint star too dim to see, or some other ordinary object hiding in the glare? It is a good question, and the answer is one of the most satisfying parts of the whole story. The reasoning comes down to mass, and to what we can and cannot see. From the way the sun-like star moves, from the size and speed of its orbit, astronomers can calculate the mass of the unseen object pulling on it, and that mass comes out to roughly 10 times the mass of our Sun. That is the first hard fact. Whatever sits at the centre of that orbit weighs about 10 solar masses. Now the question becomes simple. What could weigh 10 times as much as the Sun, and yet give off no light that we can detect? An ordinary star of 10 solar masses would be brilliant, blazing, far brighter than the Sun-like companion, impossible to miss. If it were there, we would see it easily, outshining its partner. But we see nothing, so an ordinary star is ruled out at once. There is no bright companion. There is only the warm, sun-like star and the darkness it circles. That leaves the dim and dead things, the stellar remnants, the corpses stars leave behind. Could it be a faint white dwarf, the cooling ember of a dead star? No, because white dwarfs cannot weigh 10 solar masses. There is a strict limit, a little over 1 solar mass, beyond which a white dwarf cannot exist without collapsing further. 10 solar masses is far too heavy. Could it be a neutron star, the denser corpse left by a larger star? Again, no, because neutron stars also have a mass limit, somewhere around 2 solar masses, perhaps a little more, beyond which they too must collapse. 10 solar masses is 5 times that limit. No neutron star can be that heavy. One by one, the ordinary explanations fall away. Not a normal star, too dark. Not a white dwarf, too heavy. Not a neutron star, far too heavy. Everything we know how to make, every kind of object on the menu of stellar death, is excluded, either because it would shine and does not, or because it cannot weigh as much as this thing weighs. And when you have eliminated every other possibility, what remains, however strange, must be the truth. a thing that weighs 10 times the sun, that gives off no light, that exceeds every mass limit for every kind of glowing or dead star we know of, can only be one thing: a black hole. The conclusion is forced, not by seeing the object, but by ruling out everything it could not be. This is the quiet power of the method. We never see the black hole, we see only the star and the star's motion, and the mass that motion implies, and the absence of any light from that mass, and from those facts alone, with no escape, the existence of the black hole follows. It is detective work of the purest kind, a conclusion reached by elimination, as certain as anything in astronomy. So when astronomers say there is a black hole 1600 light-years away, they are not guessing, and they are not seeing it directly. They are reasoning carefully and rigorously from what the star does and what the darkness does not do, to the only object that fits. The case is as tight as a case can be. The dark thing is too heavy to be anything that shines, too heavy to be any dead star that does not, and so it must be the one object that can be that heavy, and still give off nothing at all. The nearest black hole to the Earth was found not by sight, but by the relentless logic of elimination, the oldest and surest tool in the detective's kit. No one expects that you could prove the existence of an invisible object simply by weighing it and ruling out everything else, but that is exactly how Gaia Black Hole 1 was confirmed. No one predicts how cleanly the alternatives fall away: the bright star too dark, the white dwarf and neutron star far too heavy, until only a black hole remains. And absolutely no one anticipates how certain the conclusion becomes, reached not by seeing the darkness, but by the relentless logic that nothing else could possibly be there. Now we come to the deepest strangeness of Gaia Black Hole 1, the reason its title says it should not be able to exist. Because the way this black hole sits with its companion star is genuinely difficult to explain. It does not fit the story we tell about how such pairs are supposed to form, and the astronomers who found it said so plainly. It is, in their words, not easily accommodated by standard models of how these systems evolve. To understand the problem, we have to understand how a black hole like this is supposed to form alongside a companion star. A black hole of 10 solar masses does not appear from nothing. It is the corpse of a massive star, a star far larger than our Sun, that lived fast, burned through its fuel and collapsed at the end of its life. So in a system like Gaia Black Hole 1, there were once two stars born together. One of them was enormous, the star that would eventually become the black hole. The other was the smaller, sun-like star we still see today. And here is the trouble. Before the massive star collapsed into a black hole, it would have gone through a phase of swelling up, expanding enormously, becoming a vast bloated giant, a supergiant, far larger than its original size before finally collapsing. And that swelling is the problem. Because the Sun-like companion orbits at only about the distance of the Earth from the Sun. When the massive star swelled into a supergiant, before its collapse it would have expanded so enormously that it should have swallowed the companion star entirely, or at least engulfed its orbit. The Sun-like star should have found itself inside the bloated outer layers of its giant companion, and when that happens, when one star ends up inside the swollen envelope of another, the consequences are dramatic. The engulfed star plows through the giant's outer layers, and the friction drags it inward, spiraling it down toward the core while blowing away the giant's envelope. This process, called the common envelope phase, almost always ends with the two stars either merging into one, or with the smaller star spiraling into a much tighter orbit, ending up far closer than it began. Tonight we're going to slow down on how a black hole like Gaia Black Hole 1 forms in the first place, because understanding the normal story is what makes its puzzle so sharp. A stellar black hole, like the 10 solar mass one we have been discussing, is the corpse of a massive star. Stars shine by fusing light elements into heavier ones in their cores, the energy of that fusion pushing outward against the relentless inward pull of gravity. For most of a star's life this balance holds, the outward push of fusion exactly countering the inward pull of gravity, and the star is stable. But a massive star burns through its fuel quickly, in just a few million years, far faster than a modest star like our Sun, which will last 10 billion years. And when the fuel runs out, the balance breaks. There's nothing left to push outward, and gravity wins. What happens next depends on how massive the star is. For a star like our Sun, the collapse halts at a small, dense remnant called a white dwarf. For a heavier star, the collapse goes further, crushing the core into a neutron star, an object the size of a city holding more than a sun's worth of mass. But for the most massive stars, even the neutron star cannot hold. Nothing can stop the collapse. The core falls inward without limit, crushed by its own gravity, until it disappears behind an event horizon, forming a black hole. The outer layers of the star, in many cases, are blasted away in a supernova, one of the brightest explosions in the universe, while the core vanishes into darkness. The most massive stars end not as glowing remnants, but as black holes, dark and silent, the ultimate victory of gravity over everything else. So the 10 solar mass black hole in Gaia Black Hole 1 was once a massive star, far larger than the Sun, that lived fast, burned out, and collapsed into darkness. And before it collapsed, in the last stages of its life, it would have swelled enormously. This is the key fact for the puzzle. As a massive star nears the end, it does not stay compact. It expands, swelling into a vast bloated supergiant, far larger than its original size, its outer layers ballooning out to enormous distances before the final collapse. A star that began a few times the size of the Sun might swell to hundreds of times that size, becoming one of the largest objects in the galaxy before its core gives way. And that swelling is what should have doomed the companion star in Gaia Black Hole 1, because the Sun-like companion orbits at only about the Earth-Sun distance. When the massive star swelled into a supergiant, its bloated outer layers should have reached out and engulfed the companion's orbit entirely, swallowing the Sun-like star inside the giant's atmosphere. We will look closely, in a moment, at what that engulfment should have done, and why it makes the survival of the companion so hard to explain. But the foundation is this. A black hole forms from the collapse of a massive star, and before that collapse the star swells enormously, and that swelling, in a close pair like Gaia Black Hole 1, should have devastated the companion. The normal story of how these black holes form is, in this system, exactly the source of the mystery. No one expects that the formation of a black hole would begin with a star swelling to hundreds of times its original size, but that is what massive stars do before they collapse. No one predicts that this swelling, harmless in an isolated star, becomes a catastrophe for any close companion, engulfing its orbit in the giant's bloated atmosphere. And absolutely no one anticipates how the perfectly ordinary story of how a black hole forms turns, in a close pair like Gaia Black Hole 1, into the very reason its configuration is so hard to explain. So by the standard story, the Sun-like companion of Gaia Black Hole 1 should not be where it is. Either it should have merged with its giant companion and been destroyed, or it should have spiraled inward to a very tight orbit, ending up far closer to the black hole than the Earth is to the Sun. What it should not be is where we actually find it, in a wide, comfortable, nearly circular orbit at about the Earth-Sun distance, untouched, as though the violent swelling and collapse of its companion had barely disturbed it at all. The orbit we observe is exactly the kind that the standard formation story has the hardest time producing. The star survived something it should not have survived, and ended up in a place it should not be. Tonight, we're going to do something different for a few minutes, and simply imagine being there, in the Gaia Black Hole 1 system, watching the Sun-like star circle its dark companion, because we have described it in numbers, and it deserves at least once to be pictured as a place. Picture yourself drifting in that system, 1600 light-years from Earth. There is the star, ordinary and warm, much like our own Sun, glowing yellow-white, shining steadily into the dark. It looks, in every way, like a normal star, the kind that might warm a world and nurture life, and it is moving, slowly, in a great circle, taking about 6 months to complete one orbit. But here is the strange thing. Look at the centre of its orbit, the point it is circling, and there is nothing there. No star, no glowing object, no companion you can see. Just empty space, dark and unremarkable. The star is circling a patch of darkness, orbiting nothing visible at all. But the nothing is not nothing. At the centre of that orbit, invisible, is the black hole. 10 times the mass of the Sun, crushed into a sphere of darkness only 40 miles across, an event horizon so dark that no light escapes it. If you drifted closer to that centre, you would see, perhaps, the faintest distortion. The way the black hole's gravity bends the light of the stars behind it, warping the background sky into subtle arcs and rings around an invisible point. That subtle warping would be the only sign of the monster, a faint lensing of the distant stars, a small region where the sky itself seems gently bent around nothing. And at the heart of that distortion, the event horizon, the surface of perfect darkness, the point of no return, holding the warm sun-like star in its grip from across the distance of the Earth to our own Sun. It is a haunting image when you let it settle. A warm, ordinary sun-like star, the kind around which worlds might form and life might arise, bound forever to a dark and silent monster, circling it in the void, orbiting a darkness it cannot see. The star shines on, warm and bright and apparently normal, utterly unaware, if a star can be said to be aware of anything, that its companion is a black hole, that it has been circling for perhaps billions of years, the crushed corpse of a star far greater than itself. The light and the darkness, bound together, turning slowly through the void, the bright star and the dark hole, partners in an endless quiet dance. And somewhere out there, 1,600 light-years away, this dance is happening right now, or rather, was happening 1,600 years ago, when the light now reaching us left the star. The warm star still circles its dark companion, still shines into the void, still traces its 6-month orbit around the invisible monster, exactly as it has for ages, exactly as it will for ages more. We cannot see the black hole. We can only see the star and the way it moves, and from that know that the darkness is there, holding its bright partner in the long, slow dance that we, 1,600 years and 1,600 light-years away, have only just learned to perceive. No one expects a warm, ordinary, sun-like star to be bound forever to an invisible black hole, circling a darkness it cannot see, but that is the dance of Gaia Black Hole 1. No one predicts that the only visible sign of the monster up close would be the faint warping of the background stars around an empty point. And absolutely no one anticipates how haunting the image is. The bright star and the dark hole, partners in an endless quiet dance, the light circling the darkness, turning slowly through the void, 1,600 light-years away. By the end of tonight, you will understand that the black holes we have been discussing, the stellar ones like Gaia Black Hole 1, are only one of 2 great families of black holes, and the other family is even more extraordinary, and one of them sits at the very heart of our own galaxy. The stellar black holes are the corpses of individual massive stars, with masses from a few times the Sun up to a few tens of times the Sun. Gaia Black Hole 1, at 10 solar masses, and Gaia Black Hole 3 at 33 are both in this family. They are scattered through the galaxy by the 100 million, the remnants of stellar death. But there is another family entirely, the supermassive black holes, and these are monsters of a completely different scale, millions or even billions of times the mass of the Sun. They are not the corpses of individual stars, they are something far larger, and how they formed is still not fully understood. And there is one of these supermassive black holes at the centre of our own galaxy. It is called Sagittarius A star, and it holds about 4 million times the mass of the Sun, sitting at the very heart of the Milky Way, about 26,000 light-years from us. Every star in the galaxy, including our Sun, orbits the center of the galaxy, and at that center sits this supermassive black hole, 4 million solar masses of darkness, around which the entire galaxy slowly turns. We have watched stars orbiting close to it, whipping around it at tremendous speeds, and from their orbits, we have weighed it precisely. We have even, as we discussed, photographed its shadow. It is the great dark anchor at the heart of our galaxy, and we, far out in a quiet spiral arm, orbit it once every 230 million years or so. So our galaxy holds both families. At its center, the single supermassive black hole, 4 million solar masses, the great anchor, and scattered through its body, the 100 million stellar black holes, the corpses of dead stars, including the nearby dormant ones like Gaia BH1. The supermassive one is far larger but far away, 26,000 light-years off at the galactic center. The stellar ones are far smaller but can be much closer, the nearest only 1,600 light-years away. Two families of darkness woven through the same galaxy, one great central monster and 100 million smaller sleepers. And there is a connection between them, a genuine open question. How did the supermassive black holes form? One idea is that they grew from stellar black holes, smaller seeds that fed and merged over billions of years into the giants we see today. Another is that they formed in some other more direct way in the early universe. The stellar black holes we are now finding nearby, like Gaia BH1, are in a sense the small building blocks, the seeds from which the great central monster may, in part, have grown. Studying the stellar black holes, mapping their population, understanding how they form and merge, helps us understand how the supermassive ones came to be. The nearby sleepers and the distant central giant are connected, two ends of a story about how darkness gathers in a galaxy. No one expects a galaxy to hold two entirely different families of black holes, the stellar sleepers and the supermassive central giant, but ours holds both. No one predicts that at the very center of the Milky Way sits a single black hole of 4 million solar masses, around which the entire galaxy, including our Sun, slowly turns. And absolutely no one anticipates how the nearby dormant black holes and the great central monster are connected. The small sleepers perhaps the very seeds from which the giant over billions of years grew. This is the genuine puzzle, and it is worth being honest that astronomers do not fully have the answer. Several ideas have been proposed. Perhaps the system was not always a simple pair. Perhaps it began as a triple system, with a third star whose gravitational influence helped arrange the final orbit in a way a simple pair could not. Perhaps there are aspects of how massive stars swell and collapse that we do not fully understand, ways for the companion to survive that our models do not yet capture. Perhaps the black hole formed in some gentler way than the standard violent collapse, disturbing its companion less than we would expect. Each of these is possible, none is confirmed. The honest situation is that Gaia BH1 sits in a configuration that our best models struggle to produce, and we are not yet sure how it got there. Before we get started, let us look more carefully at the proposed solutions to the puzzle, because while none is confirmed, they are genuinely interesting, and they show how astronomers think their way around a problem that does not fit the standard story. The first idea is that the system was never a simple pair. Perhaps Gaia BH1 began not as two stars but as three, a hierarchical triple system. In such an arrangement, a third star, more distant, could have influenced the orbit of the inner pair over long stretches of time through its gravity, nudging and reshaping it in ways that a simple two-star system never could. There is a well-studied process by which a distant third star can drive a slow oscillation in the inner orbit, changing its shape and orientation over thousands or millions of years. It is possible that such a process helped arrange the final orbit we see, allowing the Sun-like star to end up in a wide, gentle orbit that a simple pair could not have produced. Perhaps the third star was later ejected, or merged, leaving behind the puzzling pair we observe. The second idea involves the details of how the massive star swelled and collapsed. Our models of how massive stars expand at the ends of their lives and how their companions interact with the bloated envelope are sophisticated but not perfect. It is possible that there are aspects of this process we do not fully capture, ways for a companion to survive the engulfment or to avoid spiraling inward as much as we expect, that our current models miss. The common envelope phase, in which one star ends up inside another's swollen atmosphere, is one of the genuinely difficult and uncertain areas of stellar physics, hard to model precisely. Perhaps, when we understand it better, the survival of the companion in Gaia Black Hole 1 will turn out to be possible after all within physics we simply have not yet fully worked out. The third idea is that the black hole formed more gently than the standard violent collapse. When a massive star collapses, the resulting supernova can give the newborn black hole a kick, a sudden change in velocity which would disturb the orbit of any companion. But if the collapse was gentle, if the star perhaps collapsed more directly into a black hole without a powerful explosion, then the companion's orbit might have been disturbed less than we would expect. A gentler birth for the black hole could leave the companion in a calmer orbit, closer to what we observe. This too is possible, and it connects to genuine open questions about how, and how violently, the most massive stars actually collapse. What I find valuable about all of this is the honesty of it. Astronomers found a system that does not fit their standard models, and rather than forcing it to fit or ignoring the problem, they laid out the difficulty plainly and proposed several possible solutions, none of which they claim to have proven. This is science working as it should, acknowledging a genuine puzzle, exploring the possibilities, and admitting what is not yet known. Gaia Black Hole. One does not break physics. It reveals a gap in our understanding, a place where our models are incomplete, a system that will push us to understand the formation of black holes and their companions better than we do now. The puzzle is not a failure. It is an invitation. No one expects a single discovery to expose a real gap in our understanding of how black holes and their companions form, but Gaia Black Hole 1 does exactly that. No one predicts which of the proposed solutions, a triple system, gentler collapse, or physics we have not yet captured, will turn out to be right, and the honest answer is that we do not yet know. And absolutely no one anticipates how valuable such a puzzle is, not a failure of science, but an invitation, a system that does not fit, pushing us to understand the dark monsters and their companions more deeply than before. Expectation. A sun-like star orbiting close to a 10 solar mass black hole should have been destroyed, or dragged inward, by the violent swelling of the star that became that black hole. Reality. The star sits calmly in a wide, gentle orbit, apparently untouched, in exactly the configuration the standard story finds hardest to explain. The nearest black hole to the Earth is also, in a real sense, one we do not fully understand, a pairing that should not be there, and yet is. No one expects the nearest black hole to the Earth to be one that defies our models of how it formed, but that is exactly what Gaia Black Hole 1 is. No one predicts that a sun-like star would survive being engulfed by the swelling supergiant that became its black hole companion, and yet there it sits, untouched, in a wide and gentle orbit. And absolutely no one anticipates how the closest black hole to us would turn out to be not just a discovery, but a genuine mystery, a system that, by the rules we thought we understood, should not be able to exist. Gaia Black Hole. 1 was only the beginning, because once astronomers had found one dormant black hole this way, by the wobble of its companion, they kept looking, and they found more. And the more they found, the clearer it became that we'd been missing an enormous hidden population of these objects, scattered through the galaxy, dark and silent, all around us. There is an even more elusive kind of black hole than the dormant ones in Gaia Black Hole 1, and it is worth understanding because it represents the ultimate challenge in finding these objects and a recent triumph in overcoming it. The truly solitary black hole, drifting alone, with no companion at all. Gaia black hole. One, dark and silent as it is, has one thing that makes it findable: a companion star. The whole method depends on watching the wobble of that orbiting star. But most black holes do not have a visible companion. Of the 100 million black holes in the galaxy, the vast majority are not in pairs at all. They drift alone through the galaxy, solitary, with no star orbiting them to betray their presence. These are the truly invisible ones, the rogue black holes, wandering the dark with nothing to give them away. They have no companion to wobble, no gas to feed on, no light of any kind. They are, in the most complete sense possible, undetectable, or nearly so. But there is one way in principle to find even a solitary black hole, and it is exquisitely subtle. It relies on the fact that gravity bends light. When a massive object passes directly in front of a more distant star, its gravity bends and focuses the light of that background star, briefly brightening it, like a lens passing in front of a distant lamp. Astronomers call this gravitational microlensing. And a solitary black hole drifting through the galaxy will occasionally by chance pass directly in front of a distant star, and for a brief time its gravity will magnify that star's light, betraying the black hole's presence not by anything it emits, but by the way its gravity warps the light of something behind it. The black hole reveals itself for a moment purely as a lens. This is fantastically difficult, because it requires a chance alignment, a solitary black hole passing almost exactly in front of a distant star, which is rare and unpredictable. But it has been done. In recent years, astronomers, watching millions of stars for the telltale brightening of microlensing, detected an event that, after years of careful follow-up, appeared to be caused by a solitary black hole, a wandering, isolated black hole with no companion, drifting through the galaxy, revealed only by the way it briefly magnified the light of a star far behind it. It was, by some accounts, the first detection of a truly solitary stellar black hole, one with no companion at all, the most invisible kind of object finally caught for a moment as a gravitational lens. So between Gaia, finding dormant black holes by the wobble of their companions, and microlensing, finding solitary black holes by the way they bend light, astronomers are beginning to reach even the darkest, most hidden members of the population. The dormant black holes with companions are the first to fall. The solitary ones drifting alone are harder, but not impossible, betrayed by the chance alignments of microlensing. Slowly, by these different methods, the 100 million hidden black holes are beginning to come into view, even the most solitary and silent of them. The wanderers with nothing at all to give them away except the gravity they can never hide. No one expects a black hole drifting completely alone, with no companion, to be findable at all, but microlensing can catch even these solitary wanderers. No one predicts that a black hole could reveal itself purely by bending the light of a star behind it, briefly magnifying it as it passes, and absolutely no one anticipates how. Between the wobble method and the lensing method, even the most invisible black holes, the solitary wanderers with nothing to betray them, are finally beginning to be found. Soon after the first discovery came a second, Gaia Black Hole 2. This one is a little farther away, around 3,800 light-years, and its companion is not a sun-like star but a red giant, a swollen, aging star, circling the black hole in an even wider orbit than the first system, Gaia Black Hole. 2 confirmed that the first was not a fluke, that there really is a population of these dormant black holes to be found, betraying themselves by the motions of their companion stars. 2 dormant black holes, found in quick succession in our own galactic neighbourhood, both of them silent, both of them previously invisible. Tonight we're going to pause in the middle of all these numbers and let the scale of what we are discussing settle into something the body can hold, because the distances and quantities are so large that they can stop meaning anything, and that is a loss worth resisting. Start with the distance. Gaia black hole. One is about 1600 light-years away. A light-year is the distance light travels in a year, about 6 trillion miles. So the nearest black hole is roughly 1600 times 6 trillion miles away, a number with so many zeros that it stops being a number and becomes just a word for far. Let me try a different approach. The light reaching us from Gaia black hole 1's companion star tonight left that star around the time the Roman Empire was in its later centuries, around the time of the fall of Rome. It has been travelling toward us, across the dark for 1600 years, the entire span from the ancient world to now, just across the distance to the nearest black hole, and that is the nearest one. The closest of all the dark monsters is so far away that its light is older than most of recorded history, now the size of the black hole itself. Gaia black hole. One holds about 10 times the mass of our Sun, and our Sun holds more than 300,000 times the mass of the Earth. So this black hole contains the mass of more than 3 million Earths, and all of that mass is packed into an event horizon only about 40 miles across, smaller than many cities. Imagine the mass of 3 million Earths, crushed into a sphere you could drive across in an hour, so dense that not even light can escape it. That is the object at the heart of this system, the dark partner of an ordinary sun-like star, and the population. 100 million black holes scattered through a galaxy, 100,000 light-years across. Try to picture that. If you could somehow see all the black holes in the galaxy, dark spots against the bright stars, the Milky Way would be salted with 100 million of them, woven through the 300 billion stars, dark companions hiding everywhere. The nearest, at 1600 light-years, is just the closest of an enormous hidden multitude, the first few of which we're only now beginning to find. The galaxy you live in is not just the bright tapestry you see. It is also this dark population, 100 million sleeping monsters woven invisibly through the light. Pattern interrupt. Hold all three together, because together they reframe the night sky. The nearest black hole, 1600 light-years away, its light older than recorded history. The black hole itself, 3 million Earths worth of mass crushed into a city-sized sphere of darkness, and 100 million more like it, scattered through the galaxy, the nearest just the closest of a vast hidden swarm. The sky above you holds not only the stars you can see, but this dark, silent, invisible population, turning quietly through the galaxy all around you, near and numerous and unseen. No one expects the nearest black hole to be so far that its light is older than the fall of Rome, but 1600 light-years is exactly that distance. No one predicts that 10 suns worth of mass, 3 million Earths, could be crushed into a sphere the size of a city. And absolutely no one anticipates how the night sky holds, woven invisibly through its bright stars, 100 million dark sleepers, the nearest just the closest of an enormous hidden multitude turning quietly all around us. And then came the most dramatic of all, Gaia Black Hole 3. This one is special. It sits about 1900 light-years away, making it the second closest black hole to the Earth, just slightly farther than the first. But its mass is what makes it extraordinary. Gaia Black Hole 3 is about 33 times the mass of our Sun. 33 solar masses. That makes it, by a wide margin, the most massive stellar black hole ever found in our galaxy. A true heavyweight, far larger than the 10 solar mass black holes we'd been finding. A sleeping giant, astronomers called it. A dormant black hole of 33 solar masses, lurking less than 2,000 light-years away, that nobody had noticed until the gentle wobble of its companion star gave it away. The most massive stellar black hole in the Milky Way, and it was hiding, silent and dark, practically in our backyard. There is another way we have learned about stellar black holes in recent years, a completely different method from anything we have discussed, and it connects beautifully to Gaia Black Hole 3 and its great mass. It is the detection of gravitational waves. When two black holes orbit each other and finally collide, merging into one, they release an enormous burst of energy, not as light, but as ripples in the fabric of space-time itself. These ripples, called gravitational waves, spread outward across the universe at the speed of light, stretching and squeezing space as they pass. They were predicted by Einstein a century ago, and for decades they were thought to be far too faint to ever detect. But in 2015, after decades of effort, instruments of extraordinary sensitivity caught one for the first time, the ripples from two black holes colliding more than 1 billion light-years away. It was a landmark in the history of science, an entirely new way of sensing the universe, not by light but by the trembling of space-time. And the black holes that gravitational wave detectors have found colliding turn out to be surprisingly massive. Many of them are in the heavyweight range, tens of solar masses, far more massive than the typical 10 solar mass black holes found in X-ray binaries. For a while, this was a puzzle. Where did all these massive black holes come from? The X-ray binaries had suggested black holes were typically around 10 solar masses, but the gravitational wave detections kept finding much heavier ones, 20, 30, even more solar masses, colliding in distant galaxies. The two methods seem to be finding different populations. Gaia Black Hole 3 helps connect them. At 33 solar masses, it is a local example of exactly the kind of heavyweight black hole that gravitational wave detectors keep finding far away. And its old, metal-poor companion confirms how such massive black holes form, from ancient metal-poor stars that lose little mass before collapsing. So the heavyweight black holes colliding in distant galaxies, the ones gravitational waves reveal, and the sleeping giant in our own backyard found by Gaia, are members of the same family, formed the same way, from the same kind of ancient metal-poor stars. The two completely different methods, gravitational waves and astrometry, are converging on the same picture of where the most massive stellar black holes come from. This is one of the most satisfying things in science, when two entirely independent methods, sensing the universe in completely different ways, one by ripples in space-time, the other by the wobble of stars, arrive at the same conclusion. The gravitational wave detectors hear the heavyweight black holes colliding across the universe. Gaia sees one sleeping in our own neighborhood, and together they tell the same story, of massive black holes forming from ancient metal-poor stars, scattered through the cosmos, ringing space-time when they collide and wobbling their companions when they sleep. The nearest black holes and the most distant collisions are illuminating each other, two windows onto the same hidden population. No one expects two completely different methods, gravitational waves and the wobble of stars, to converge on the same picture of where massive black holes come from, but that is exactly what is happening. No one predicts that the sleeping giant in our backyard would be a local cousin of the heavyweight black holes colliding across the universe, and absolutely no one anticipates how the trembling of space-time and the dance of stars, two utterly different ways of sensing the cosmos, are illuminating the same hidden family of dark monsters. Tonight, we're going to give Gaia Black Hole 3 its own moment, because it is the most spectacular of the discoveries, and the reason it is so massive tells us something deep about where the biggest black holes come from. Gaia. Black Hole 3 was announced in the spring of 2024, and it immediately set a record. At about 33 times the mass of our Sun, it is the most massive stellar black hole ever found in our galaxy. The black holes we had been finding by other means were typically around 10 solar masses, the kind of mass you get from the collapse of a fairly ordinary massive star. 33 solar masses is in a different league, a true heavyweight, far more massive than astronomers expected to find lurking nearby. And like the others, it is dormant, silent, dark, betrayed only by the wobble of its companion star. A sleeping giant, the astronomers called it, and the name fit. But the most interesting thing about Gaia Black Hole 3 is not just its mass. It is its companion, and what that companion reveals. The star orbiting this black hole is old, and it is what astronomers call metal poor, meaning it contains very few elements heavier than hydrogen and helium. This tells us that the system is ancient, formed long ago in the early days of the galaxy, when the universe had not yet been enriched with many heavy elements. And here is the connection. Astronomers had long suspected that the most massive stellar black holes should form from stars that are themselves metal poor. The reason is subtle but important. Stars with more heavy elements have stronger stellar winds, blowing more of their mass away over their lives, so they end up with less mass to collapse into a black hole. But metal-poor stars, lacking those heavy elements, have weaker winds, lose less mass, and so can collapse into more massive black holes. The fewer the heavy elements, the bigger the black hole. So Gaia Black Hole 3, with its old, metal-poor companion, is exactly the kind of system where the most massive black holes were expected to form. Its great mass is not a fluke. It is a confirmation, a direct example of the predicted link between metal-poor stars and massive black holes, found right in our own galactic neighbourhood. The 33 solar mass black hole is so massive precisely because it formed from an ancient, metal-poor star in the early galaxy that lost very little of its mass before collapsing. The discovery did not just find the biggest stellar black hole nearby, it confirmed a long-standing idea about why the biggest black holes are big. And this connects to something larger, to the black holes detected in distant galaxies by gravitational waves. When black holes collide far across the universe, they send ripples through space-time that our instruments can detect, and many of those colliding black holes have turned out to be surprisingly massive, in the same heavyweight range as Gaia Black Hole 3. Astronomers had wondered where such massive black holes come from. Gaia Black Hole 3, found nearby with its metal-poor companion, is a local example of exactly this kind of heavyweight black hole, a nearby cousin of the massive ones colliding in distant galaxies, and a clue to how they all form. The sleeping giant in our backyard helps explain the giants ringing space-time across the cosmos. No one expects the most massive stellar black hole in the galaxy to be hiding less than 2,000 light-years away. But Gaia Black Hole 3 is exactly that. No one predicts that its great mass would be explained by its ancient metal-poor companion, confirming the long-suspected link between metal-poor stars and massive black holes. And absolutely no one anticipates how this nearby sleeping giant connects to the heavyweight black holes colliding in distant galaxies, a local clue to where all the biggest black holes come from. These three discoveries, in just a few years, point towards something profound and a little staggering. They are almost certainly the nearest examples of a vast hidden population. Astronomers estimate that our galaxy contains something like 100 million stellar mass black holes. 100 million. The corpses of all the massive stars that have lived and died across the history of the galaxy, each one a black hole scattered through the stars, and the overwhelming majority of them are dormant, isolated or in wide orbits, not feeding on anything, giving off no light at all. They are, almost all of them, completely invisible. For all of the history of astronomy, we could only find the rare loud ones, the feeding X-ray binaries. The 100 million dark sleeping ones were beyond our reach. We knew from theory that they had to be out there, but we could not see a single one. Before we get started on the wider picture, it is worth pausing on the distance itself, on those 4 words, 1600 light-years, because numbers like that wash over us so easily, and this one deserves a moment to be felt rather than just read. A light-year is the distance light travels in a year, and light is the fastest thing there is, moving at about 6 trillion miles every year. So 1600 light-years is 1600 times 6 trillion miles. A number so large it stops meaning anything as a figure. Let us try to feel it another way instead. Light from the sun reaches us in about 8 minutes. Light from the nearest star beyond the sun takes a little over 4 years. light from the center of our galaxy takes some 26,000 years, and light from Gaia Black Hole 1 takes 1,600 years to cross the gap and reach our telescopes. That means the light we're gathering now, the starlight by which we measured the wobble and found the black hole left that system 1,600 years ago. We're not seeing the black hole and its star as they are tonight. We are seeing them as they were 16 centuries past when the light began its journey. Think about what was happening on Earth 1,600 years ago when that light set out. The Roman Empire in the West was in its final decline. The Great Library of Alexandria was a fading memory. No one on Earth had any concept of a black hole or a galaxy or a light year. Whole civilizations have risen and fallen, languages have been born and died, the entire span of recorded modern history has unfolded, all in the time it took that single beam of starlight to cross the distance between Gaia Black Hole 1 and us. The wobble we measured is a 1,600-year-old message, a report from the deep past only now arriving. And yet, in cosmic terms, 1,600 light-years is nothing at all. It is right next door. Our galaxy is 100,000 light-years across. On that scale, 1,600 light-years is a single step from our doorstep, a tiny fraction of the way to the galactic center, a stone's throw in a city the size of the Milky Way. This is the strange double truth of cosmic distance. 1,600 light-years is at once impossibly far, far enough that the light is 16 centuries old, far enough that no ship we can build could ever cross it, and absurdly close the nearest known black hole, a near neighbor in a galaxy so vast that our entire neighborhood is a speck within it. Both things are true at once. The black hole is near, the nearest of its kind, and it is unreachably far, its light a message from the age of the falling empires. We hold both truths together when we say, simply, the nearest black hole to the Earth, 1,600 light-years away. And there is a quiet comfort folded into that distance, the same comfort we keep returning to. 1,600 light-years is near in the scale of the galaxy, but it is enormously, reassuringly far in the scale of any threat. The black hole cannot reach us across that gulf. Its gravity at that range is nothing to us, fainter than the pull of the nearby stars. It simply turns with its star in its distant corner of the galaxy, sending us its ancient light, while we lie safe beneath a sky that holds it at a distance no danger could ever cross, near enough to find, far enough to be utterly harmless, the nearest black hole 1,600 years away by the speed of light, and entirely, permanently beyond any power to touch us. No one expects that the light revealing the nearest black hole left its star 1,600 years ago, in the age of falling empires, only now reaching our telescopes. But that is the truth of the distance. No one predicts how a gap can be at once impossibly far, its light 16 centuries old and cosmically near, a single step in a galaxy 100,000 light-years wide, and absolutely no one anticipates how that same distance is the source of our safety, near enough to find, and far enough that the monster can never ever reach us. Gaia changed that. By measuring the positions of 2 billion stars with exquisite precision, it gave us for the first time a way to find the dormant black holes, to catch them by the wobble they induce in their visible companions. Gaia, Black Hole 1, 2 and 3 are the first few of the 100 million, the nearest ones, the first to be caught. And there are surely more to come, as Gaia gathers more data and astronomers refine their search. We are, for the first time, beginning to map the hidden black holes of our galaxy, the dark majority, the sleeping monsters scattered through the stars all around us. Before we get started on the future, it is worth knowing that the discovery of nearby dormant black holes is just beginning, that Gaia Black Hole 1, 2, and 3 are the first few of what will surely be many, and that the coming years are likely to transform our map of the galaxy's hidden darkness. The reason is that Gaia keeps gathering data, and each new release of its measurements is more precise and covers a longer span of time, which makes it more sensitive to the small wobbles that reveal hidden black holes. The first dormant black holes were found in earlier, more limited data. As Gaia's full dataset is processed and released, covering the positions of 2 billion stars measured over many years, astronomers will be able to detect smaller wobbles, longer orbits, more subtle signs of invisible companions. The catalogue of dormant black holes found by their companions is expected to grow, perhaps from a handful to dozens, and eventually, as the technique matures and the data deepens, to many more. We are at the very beginning of mapping the hidden population, and Gaia is not the only effort. Other surveys watching stars for the wobbles of unseen companions are joining the hunt. The micro-lensing surveys, watching for the brief brightening caused by a black hole passing in front of a distant star, are catching even the solitary wanderers with no companion. Future missions and telescopes will push the search further still, more precise, more sensitive, covering more of the sky and more of the hidden population. The 100 million dark sleepers of our galaxy will not all be found soon, or perhaps ever, but the nearest and most detectable of them are beginning to come into view, and the catalogue will grow year by year as our instruments sharpen. There are real questions driving this work beyond simply counting. By finding and weighing many dormant black holes, astronomers can map the full distribution of their masses, testing ideas about how massive stars collapse, filling in the mysterious mass gap, understanding the link between metal-poor stars and massive black holes. By studying the orbits, they can probe the puzzle of how black holes and their companions form and survive, the very puzzle that Gaia Black Hole 1 first posed so sharply. Each new system is a data point, a test of our models, a clue to the deeper questions of stellar death and binary evolution. The growing catalogue is not just a census. It is a tool for understanding how the galaxy makes and keeps its dark monsters. So the story we have told tonight is an opening chapter, not a conclusion. Gaia Black Hole 1 was the first clear dormant black hole found by its companion's wobble, the nearest known black hole to the Earth. But it is the beginning of a new era, in which the hidden population of the galaxy, the 100 million dark sleepers, slowly comes into view, one wobbling star at a time. The nearest black hole today may not be the nearest we know of in a decade. As the search deepens, we will find closer ones, stranger ones, more of them, slowly filling in the dark map of our galaxy. We have only just begun to see the darkness woven through the light. No one expects the discovery of nearby black holes to be just beginning, but Gaia Black Hole 1, 2 and 3 are only the first few. No one predicts how the catalogue of dormant black holes will grow, as Gaia's data deepens and other surveys join the hunt, slowly mapping the hidden population. And absolutely no one anticipates how much is still to come, the 100 million dark sleepers coming gradually into view, one wobbling star at a time, in an era of discovery that has only just opened. Tonight we're going to sit with that staggering number, the 100 million black holes thought to be hidden in our galaxy, because it deserves to be understood, not just stated. Where does such a number come from? It comes from counting deaths. Across the long history of our galaxy, generation after generation of stars has been born, lived, and died. And a certain fraction of those stars, the most massive ones, end their lives as black holes. By counting how many massive stars have lived and died over the galaxy's history, astronomers can estimate how many black holes should have been left behind. The answer is enormous. Something like 100 million stellar mass black holes, the accumulated corpses of the largest stars scattered through the galaxy across billions of years of stellar death. They are not a rare exotic phenomenon. They are the natural, inevitable remnants of a process that has been happening over and over for the entire life of the galaxy, and almost all of them are invisible. This is the crucial point. Of those 100 million black holes, only a tiny handful are in the loud feeding X-ray binaries we could find before. The overwhelming majority are dormant, isolated or in wide orbits, not feeding on anything, giving off no light at all, They drift through the galaxy, dark and silent, undetectable by any method we had, until Gaia. For all of the history of astronomy, we could see perhaps a few dozen black holes, the loud-feeding few. The other 100 million minus a few dozen were completely hidden. A vast dark population that we knew, from theory, had to exist, but could not see a single member of. Think about what this means for the space around us. Our galaxy is about 100,000 light-years across, and it holds a few 100 billion stars. If there are 100 million black holes scattered through it, then black holes are not vanishingly rare. They are woven through the population of stars, with a black hole, on average, somewhere within a few dozen light-years of any given point. The nearest black holes to us, like Gaia Black Hole 1 at 1600 light-years, are not freakishly close. They're about what you would expect, given how many of these dark sleepers there are. There are almost certainly black holes closer to us than Gaia Black Hole 1, dormant ones we have not yet found, hidden in the dark, waiting for their companions to give them away, or simply drifting alone where no companion can ever reveal them. This is, in a way, the deepest message of the whole discovery. Not just that there is a black hole 1600 light-years away, but that the galaxy we live in is full of them, 100 million dark sleepers, and we are only now beginning to find them. Every method we develop, every refinement of Gaia's data, will reveal more, slowly mapping the hidden population, the dark corpses woven through the bright stars. We have lived our whole history beneath a sky that we thought we understood, a tapestry of stars, and only now are we learning that woven invisibly through it are 100 million black holes, the dark majority, finally beginning to come into view. No one expects our galaxy to hold 100 million black holes, but that is the number the accumulated deaths of massive stars imply. No one predicts that almost all of them would be invisible, dormant and dark, a vast hidden population we knew had to exist but could not see. And absolutely no one anticipates how this transforms the space around us, from a sparse scattering of distant monsters into a galaxy salted with 100 million dark sleepers, the nearest of them surely closer even than the ones we have found. Pattern interrupt. Let the scale of that settle, because it changes the feel of the night sky. 100 million black holes scattered through our galaxy, almost all of them dark and silent and invisible, and the nearest ones only 16 and 1900 light-years away, in our own quiet neighbourhood. They are not rare, distant, exotic monsters confined to the violent centres of galaxies. They are everywhere, common, woven through the population of stars, dark companions hiding in plain sight, betrayed only by the gentle dance of the stars that circle them. The galaxy is not just full of stars, it is full of their dark corpses too, 100 million sleeping black holes, and we are only now, for the first time, learning to find them. By the end of tonight, it helps to know not just how far away Gaia Black Hole 1 is, but where it sits, in what part of our galaxy this nearest dark neighbour turns, because placing it on the map makes it feel less like an abstraction, and more like a real address in a real city of stars. We live in the Milky Way, a vast spiral of several 100 billion stars, a flattened disk 100,000 light-years across, wound into great arms that curl out from a bright and crowded centre. Our sun is not near that centre. We live far out in the suburbs, about 26,000 light-years from the core, in a quieter region between two of the great spiral arms, in a smaller spur of stars sometimes called the Orion Arm, or the Local Arm. It is a calm neighbourhood, as galactic neighbourhoods go, away from the crowded violence of the centre, away from the densest clusters and the fiercest stellar nurseries, and it is here, in our own local arm, in our own quiet stretch of the galactic suburbs, that Gaia Black Hole 1 turns, 1600 light-years from the Sun, in the direction of a constellation we can find in our own night sky. 1600 light-years, on the map of the galaxy, keeps the black hole firmly within our local neighbourhood. It is not in some distant arm, not near the seething centre, not in another part of the galaxy entirely. It is here, among the stars that are in the broadest sense our near neighbours, the stars of our own corner of the Milky Way. When you look up at the night sky and pick out the familiar constellations, the patterns drawn by the nearer, brighter stars, you're looking at our local neighbourhood, and somewhere in that direction, far too faint and far too dark to see, the nearest black hole keeps its station, woven invisibly among the visible stars, part of the same local crowd, just darker and quieter than all the rest. There is something that reorders your sense of the sky in that thought. We're used to imagining black holes as distant and exotic, things that belong to the violent hearts of galaxies or the deep reaches of space, far removed from our gentle local stars. But Gaia Black Hole 1 is not far removed. It is a member of our own galactic neighbourhood, turning among the same stars we have named and mapped and watched for thousands of years, a dark resident of the local arm, a near neighbour that simply happens to give off no light. The familiar sky, it turns out, has darkness threaded all through it, hidden among the points of light, and at least one of those dark threads, the nearest we have found, lies right here in our own quiet corner of the spiral. So, when we say the nearest black hole to the Earth, we are not pointing towards some remote and alien region of the cosmos. We are pointing into our own neighbourhood, into the local arm of the Milky Way, into the same stretch of the galaxy that holds our Sun and our familiar stars. It is close in every sense that matters for belonging, a neighbour in our local crowd sharing our corner of the great spiral, turning quietly among the stars we know. The darkness, it turns out, does not live only in distant and dramatic places. Some of it lives right next door, in the calm suburbs of the galaxy, among the gentle local stars, the nearest of the hidden monsters keeping its station in our own familiar sky. No one expects the nearest black hole to be a resident of our own quiet galactic suburb, turning among the same local stars we have mapped for thousands of years, but that is exactly where Gaia Black Hole 1 sits. No one predicts that the familiar night sky has darkness threaded all through it, hidden among the visible points of light, and absolutely no one anticipates how the nearest of the hidden monsters keeps its station right here in our own corner of the spiral, a dark neighbour in the calm suburbs of the Milky Way. No one expects our galaxy to contain 100 million black holes, almost all of them invisible, but that is what the estimates say, and Gaia is beginning to confirm it. No one predicts that the nearest ones would be found not at the violent galactic centre, but in our own quiet neighbourhood, 16 and 1900 light-years away, dormant and silent. And absolutely no one anticipates how thoroughly this rewrites the night sky from a tapestry of stars into something stranger, a galaxy salted with 100 million dark sleeping monsters, the nearest of them practically next door. Before we get started, let us address the worry directly, because it is the natural one, and the honest answer is deeply reassuring. Should we be afraid of a black hole 1600 light-years away, and of the 100 million others scattered through the galaxy? The simple answer is no, not in the slightest, and it is worth understanding why, because the reasons are solid. First, 1600 light-years is an almost unimaginable distance. Light, the fastest thing in the universe, takes 1600 years to cross it. The fastest spacecraft we have ever built would take tens of millions of years to make the journey. Gaia Black Hole. One is so far away that it has no physical effect on us whatsoever. Its gravity at that distance is utterly negligible, far weaker than the gravity of the nearby stars, which is itself far too weak to matter. It is not pulling us toward it. It is not affecting our solar system in any way. It simply sits there, 1600 light-years off, holding its single companion star, completely irrelevant to us. Second, a black hole is not a cosmic vacuum cleaner. This is one of the most common and most understandable misconceptions, and it is worth dispelling clearly. A black hole does not roam through space sucking everything in. its gravity is exactly the same as the gravity of any object of the same mass. If you replaced our Sun with a black hole of the same mass, the Earth would not get sucked in. It would continue in exactly the same orbit, as if nothing had changed, just colder and darker. A black hole is only dangerous if you get very close to it, far closer than any star ever gets to its neighbours. From any normal distance, a black hole is just a massive object you would orbit, no greedier than a star. Gaia black hole. One holds its companion in a stable orbit precisely because, at that distance, it behaves just like an ordinary massive object. It is not devouring the star, it is simply holding it gently in orbit. Third, black holes do not move toward us in any threatening way. They drift through the galaxy, yes, like all stars, on slow orbits around the galactic centre, but they do not hunt, do not steer, do not approach. The chance of a black hole drifting close enough to our solar system to cause any trouble, over any timescale that could matter to us, is vanishingly, almost incomprehensibly small. The galaxy is vast, and even 100 million black holes are spread so thinly through it that the odds of one coming near us are negligible. We are as safe from the dark sleepers as we are from anything in the cosmos, which is to say, completely, by the simple, overwhelming fact of distance. So you can set the worry down entirely. The discovery of nearby black holes does not make the universe more dangerous to us. It does not bring any threat closer. The black holes were always there, 100 million of them, woven through the galaxy. We simply could not see them before. Now we can see a few of the nearest, and they are exactly as harmless as they always were, dark sleepers in the deep distance, holding their companions, drifting slowly through the galaxy, threatening nothing. The galaxy is richer and stranger than we knew, full of hidden monsters. But the monsters are sleeping and far away, and they have no interest in us at all. No one expects the discovery of a nearby black hole to be completely reassuring, but it is, because distance and the nature of gravity make it utterly harmless. No one predicts that a black hole, far from being a cosmic vacuum cleaner, is no greedier than an ordinary star, dangerous only up close, harmless from any normal distance. And absolutely no one anticipates how the galaxy, full of 100 million dark sleepers, remains as safe for us as it ever was, the monsters all far away, all harmless, all simply turning quietly through the dark while we rest. So let us gather the whole journey now, gently, the way you would draw the threads of a long story together before sleep. We began with a black hole next door, Gaia Black Hole 1, the nearest black hole to the Earth that we know of, only about 1,600 light-years away, in our own quiet corner of the galaxy. And we found that it was unlike the black holes we had known before. Not a loud, feeding monster screaming in X-rays, but a dormant one, dark and silent, giving off no light at all, betraying itself only by the gentle wobble it produces in the motion of the ordinary sun-like star that circles it once every 6 months. We learned how astronomers found something completely invisible, not by seeing it, which is impossible, but by watching the dance of the star that orbits it, measured with breathtaking precision by the Gaia spacecraft, which has mapped the positions of nearly 2 billion stars across our galaxy. We learned what a dormant black hole is, a black hole at rest, not feeding, and why most of the black holes in the galaxy are exactly like this, dark and silent and invisible, while the loud feeding ones we found first are the rare exceptions. And we sat with the genuine mystery of it, the reason its title says it should not exist. The sun-like companion, orbiting at about the Earth-Sun distance, should have been destroyed or dragged inward by the violent swelling of the star that became the black hole. Instead, it sits calmly in a wide, gentle orbit, in exactly the configuration our standard models struggle most to explain. The nearest black hole to us is also one we do not fully understand, a pairing that, by the rules we thought we knew, should not be there, and yet is. We followed the discovery outward, to Gaia Black Hole 2, and to Gaia Black Hole 3, the most massive stellar black hole in the galaxy, 33 solar masses, a sleeping giant less than 2,000 light-years away. And we found that these are only the nearest few of a vast hidden population, 100 million dormant black holes scattered through our galaxy, almost all of them invisible, that we're only now, with Gaia, beginning to find. No one expects the nearest black hole to the Earth to be a silent dormant one, hiding in our own neighbourhood, found by the dance of a star, but that is exactly what Gaia Black Hole 1 is. No one predicts that our galaxy holds 100 million of these dark, sleeping monsters, the nearest of them practically next door. And absolutely no one anticipates how a single wobbling star, measured precisely enough, could reveal the closest of all the dark monsters, and through it, a whole hidden galaxy of black holes we had never been able to see. Here is the thought I want to leave you with, and it is a calm one, despite the monsters. It might unsettle you to learn that there is a black hole only 1,600 light-years away, that our galaxy is salted with 100 million of them, that the dark sleeping monsters are far nearer and far more numerous than we ever realized. But 1,600 light-years is an enormous distance, vast beyond imagining, far too far for that black hole, or any of them, to ever pose the slightest threat to us. Gaia, black hole. One is not coming for us. It is not pulling us toward it. It simply sits there, 1,600 light-years away, holding its single star in a quiet orbit, doing nothing, threatening nothing, a dark and harmless sleeper in the deep distance. The discovery does not make the universe more dangerous. It only makes it richer, stranger, more full of hidden things than we knew. And there is something almost beautiful in that, when you let it settle. The galaxy is not just the bright tapestry of stars we see. Woven through it, all around us, are these dark, silent sleepers, the corpses of ancient massive stars, 100 million of them, turning quietly in the dark, holding their companions, harming nothing, simply existing, hidden, patient, near. We are not in danger from them. We are only now beginning to see them, to know they are there, to feel the true richness of the galaxy we live in, full of light and full of darkness both, the bright stars and their dark companions turning together through the long night. The nearest black hole is sleeping, 1,600 light-years away, holding its single star in the dark. 100 million more turn quietly through the galaxy, dark and silent and harmless. And you are here, on a small bright world, beneath a sky fuller and stranger than anyone knew, safe in the vast and gentle distances of the cosmos, with the dark sleepers turning far away, harming nothing while you rest. Sleep well tonight. Good night.